Our final topic is going to be feature selection. You've presented feature selection in some of your topics, and so feature selection is essentially not using all the columns in your data set, but selectively keeping some and removing some of them. When you had your SVM homework, you ran into a problem of having too much data, and you weren't able to run it for the whole data set. It would take a long time to train your model, right? So one solution to that problem that you used was to randomly pick a subset of the data set. You randomly selected a subset of the rows and performed your modeling training on that subset. Another strategy would be selecting columns, not rows, and then only performing training on those columns. The question is, how do we select, excuse me, which columns should be used in training? So feature selection refers to making a selection from the existing features. Feature extraction represents taking your data and moving to a new space. Okay, so feature extraction sometimes can act as a way to reduce your data set, but they are sort of different things. Okay? So we learned about principal component analysis. There are some other data mapping methods where you would be extracting features rather than selecting features. So in your image processing homework, you did feature extraction. You had the pixel values, but you calculated the histogram that was feature extraction. So from the large dimensional data where you had 30 by 30 times that's 900 features, rather than using those, you just use the histogram values, which gave you a smaller number of features. Okay. The feature selection will limit to the definition of using some of the columns and not using the rest. All right. The reason we select features are several. One of them is that the features may not be easily obtainable. If you are working in a medical field, you don't want to do every possible test on a patient. You only want to do the ones that are relevant, right? Or when you go to the doctor, they measure everything anyway. But if you are, say, studying a disease and you measure on a microarray all the genes that are expressed in humans, at the end of your study, you would want to come up with a handful that can act as a biomarker. So in the clinic, rather than having to run the entire microarray for a patient, you would only want to measure those handful genes. Okay? So to identify which handful genes would give you the best success rate in terms of prediction is the topic of feature selection. When you use a smaller set of features, the interpretation of your model becomes easier as well. So think about decision trees. If you, well, they will automatically reduce the number of automatically selected features, but you will end up with a model that's more easily interpretable if you select a subset of the features. Okay. So generalization is a common problem in machine learning. If you use too many features, so if you throw in all of your data to your machine learning method and have it and hope that it will learn something from that whole set, what it's going to end up doing is it's going to end up memorizing from the features that are not really relevant to your problem. So the features, say you are studying Alzheimer's disease, and one of the features is which city the patient comes from. So you may argue whether or not that's relevant or not. But if it is not relevant, then you should not really have your model learn from it. So it may learn things that are part of your data set, but not necessarily capturing the inherent nature of the problem that you are studying. So there are some of the features you would want to throw away when you are presenting them to your machine learning method. And feature selection will help with your generalization of the learned model so that for a new sample, it will perform better. Okay. And reduced time and space requirements is an added benefit. The smaller, the fewer number of features you use, the lower computational requirements. Your program will run faster. It will require less memory. Okay. You can run it on your laptop rather than having to require a supercomputer to run it. So the feature selection can be described, can be formulated as follows. If we have F features, well, F is the number of columns in the way that we usually represent our data in this class. So our rows were samples, our columns were features. So given F columns, where F are your features, you would want to select a subset of them, such as this small k. So if you say I've already decided I'm going to keep 5 features out of the total number of features I have, say 100, I'm just going to keep 5. So out of 100 columns that you have in your data set, you want to pick 5 of them. How many different possible ways can you do that? You can do that with F combination by K. So that's F factorial divided by K factorial times F minus K factorial. Okay? So the combination is still a large number for most data sets. If you don't know K ahead of time, which you usually don't, so if you wanted to say find a handful, you'd be looking for K equals 10. But in general, you wouldn't know how many features would give you the best result. In that case, you would have to examine all subsets of features. And all subsets of features is 2 to the F different possibilities. And to sort of get that 2 to the power F number, you can consider as the different ways that you can obtain a set. So if I have F things to select from, the first thing I can either select it or not, right? That's 2 possibilities. The next thing I can either select it or not, that's 2 possibilities. And then the total number of possibilities 2 to the power F. Make sense? So if you say select none of them, that's 1 possibility. If you select all of them being 1, then that's another possibility. Right? Everything is in between is where you have some zeros and some ones in your binary vector, where this binary vector represents which features you selected from your feature set. I shouldn't say exponential here. This is a typo. Exhaustive search. Exhaustive search is a general term we use when we refer to trying out all the possibilities. All right. So 2 to the power F is clearly going to be larger than we would like to try. If F is 100, that means we would have to try 2 to the power 100 different things, different subsets, and examine which one works well, and pick the best one. Okay, so we don't have the luxury and the time, computational time, to test all of those 2 to the power F possibilities. Whenever you have a search problem and you don't want to exhaustively search all the options, you have to use an optimization procedure to give you a good enough result. The optimization function that we described earlier can be applied here, and we're going to see some examples in a few slides. So the objective function, which defines how good a candidate set is, can be described in 2 different ways. One is using a filter-based approach, where we can characterize the goodness of each feature using some statistics. And then the wrapper method, which is a term that we use to describe the classification performance of a set of features. Okay, let's give some examples. The filter methods, it'll make more sense. Okay. So if I have a filter in mind, I can calculate this filter for every feature. Say I have 100 features. I can calculate the Euclidean distance or the city distance, any distance between classes for each feature. So how well does one particular column separate the one class, the zero class, from the one class? So we did that in decision tree as well. Entropy was one such metric, right? Another approach is using the within class and between class scatters, such as the one that we use in linear discriminant analysis. So that would be another metric we can use. All right. So if I have 100 columns, I'll just take one column which contains numbers, right? I also have my target information, which tells me which samples are in one class and which samples are in the other class. So this is my clustering in a way, right? So my samples in zero class will be one group, samples in the other class will be the other group. And then I can look at the numbers here for the zero class and the numbers for the one class and see how well separated those numbers are. And these different metrics describe that well separateness of the two classes with respect to one of the features. Okay. Other features I could use are correlation. So if I have a column that is highly correlated with my target, that column should be a good column to use in a classification model, right? In the extreme case, if I have a column that's 100% correlated, so it's identical, and there's no need to use any other feature, I can just use this one. But you'll never have that. You'll have a mix of that. The correlation will not be 100%. Okay. Some other methods from information theory can also be used here, such as mutual information, which is the decrease in entropy of the class with the knowledge of having this. Okay. Similar to the idea that we used in information gain when we constructed decision tree. Okay. So these filters are per column calculations that we can do. We are not really running any machine learning method to evaluate how good a column is, how good a feature is. We are comparing the numbers for that feature with our target to evaluate how good a feature is by itself. Make sense? Okay. There are a large number of filter descriptions. Mutual information is commonly used as one, and t-statistic is another one that you can use over correlation. Okay. So what's a t-statistic? You can actually run a statistical test, taking the numbers for your zero class, taking the numbers for your other class, perform a t-test. If the p-value is small, that means for that feature itself can separate the data very well. Okay. So the smaller the p-value, the better a feature is for the purpose of classification. All right. So the problem with the filter methods is that you are not capturing the combined effect of filters. So I can decide just by using filter methods which of these columns to pick by themselves, right? But then when I ask the question, which pair of columns should I pick? It's not as clear cut, right? So if I pick one with a very good p-value, and then the next one with a very good p-value is not necessarily the best feature, okay? Because it may have exactly the same information as this one. It's not giving me any additional information for classification purposes. Okay. All right. So once we have these filter methods, even for the wrapper methods, let's see if I have the wrapper methods. Okay, so let me go back and describe what a wrapper is. So what we would do in the wrapper method is actually run a machine learning method and evaluate the performance, evaluate the cross-validation performance. Okay. So what I would, for example, do is take each column and pretend my data is just one column. And then run, say, SVM, try to predict this target from just this column. And then ask what's my cross-validation accuracy. So I get 80% from this 80% accuracy, cross-validation accuracy, if I just use this column. And then I'm going to move on to the next column and ask the same question. If I were to use just this one, what would be my cross-validation accuracy? And say 70%, and so on. I'm going to evaluate each one and pick the one that works best. Okay? And I can set it aside, go through the rest of the features, and ask the question, which one should I use in combination with this one that will give me the best combined cross-validation accuracy? So this strategy is called forward search. I'm starting with nothing, and I keep adding one feature at a time until I get enough accuracy. Okay. The pros and cons of filters and wrappers are the following. Filters are, you can execute efficiently. You don't need to run a machine learning method every time. That may include cross-validation, looking at your entire data set, training an SVM model, so very computationally time and memory intensive. Okay. They can generalize well because they evaluate the intrinsic properties of the data. The problem is they have a tendency to select large subsets. So they end up selecting many features from your feature set. Okay. The wrappers are more accurate. So if you can use wrappers, if you have enough time, enough computational time, you can wait long enough to run a wrapper, run a wrapper. Okay. If your data set is too large for a wrapper method to handle, then use a filter method. So that's sort of the general guideline. They are very accurate. They have a lack of generality, and I would say that slow execution is the biggest bottleneck for wrapper methods. Okay. All right. And this lack of generality, doesn't really refer to the generalizability of the model. It's rather representing the use of a subset of features in one machine learning method versus another. So say if you are using support vector machine and you end up discovering that some of these features work well. Those same features may not be the best features if we were to use say decision trees. Okay? So depending on your machine learning model that you use, you have to rerun your wrapper to identify the best set that works for that particular machine learning method. Okay. All right. So I described this strategy, the forward strategy, where you add one feature at a time. That has problems, right? It may not find the best combination because early on I may make a bad choice, and then it makes it so that I'm not able to explore all possible subsets. So the nice approach is to order features by the individual goodness and then keep the top K. And this individual goodness can be based on either a filter method or a wrapper method. I can go through each column, identify how good it is, how well it separates my data using a filter method, or how well it performs in, say, support vector machines, and then look at their accuracy or look at their filter metric and keep the top, say, 10, where you would need a predefined idea of what K will be. Okay? So the drawback is that worse features may be better in combination. All right. So there may be a feature that is not as good as the other ones if you look at them individually, but there may be two really bad features, but when you combine them, they may separate your data very well. Okay, so you would be missing on those pairs of or combinations of features using this naive approach. The exponential algorithms will try to explore a more complete search space. Okay. The exhaustive search is only applicable if the number of features is small. Say if you have 10 features total and you want to find out which subset would work well, you can use an exhaustive search because to the power 10, you have 1,000 combinations to go through, so that's feasible. Okay. So if the number of features is small, you can do exhaustive search where you can try all possible combinations. Branch and bound is the name of a general algorithm where you explore the search space in a tree-like structure, and when things stop improving, you backtrack. Okay. So, for example, as it applies to feature selection, I can do the following. I'm going to call my features A, B, C, D. Okay. At the top level, I have not selected anything, right? So I'm going to start with no features at all, and you can actually run a machine learning model with no features at all. And then what it will learn is the average, right? So if your targets are these, one option is to use an empty matrix for your input matrix. X equals as many rows as your target, but 0 columns. Okay. And what the machine learning method will learn from that is what percentage of your targets are ones and what percentage are zeros, and it will usually give you always a 1 or always a 0, depending on which one you have more. Okay, so that's your sort of base case with no features. In the branch and bound, what we do is at the top node we say, okay, I'm not going to select anything, and then you would individually test them. And then we're going to select A, and then with this I have some accuracy. When I add A, does the accuracy improve? If it does, then I'm going to keep expanding A. To A, which other feature should I add? Let's say when I add D, it makes an improvement to 90%, and then it stops there. And the assumption, I'm going to make an assumption that adding a feature will improve the result, and it will saturate. Adding more features will not decrease the result, which is not realistic, but for the explanation, I'll keep it that way. So then I'm going to stop here, or you can go and add all the features, but then you're going to come back to the top and say what happens if I select B. Okay. I already know an answer that has 90%. All right. So I should, if B cannot give me an answer above 90%, I'm going to stop. I'm going to expand. I know the best. I know the best case and the worst case. So I'm going to keep track of the best I've seen so far and the worst I've seen so far. And as I expand in the other branches, if it's hopeless, I'm going to stop the search. Okay, I'm not going to expand the search anymore. So that makes it so that instead of examining all possibilities, I can sort of prune out this tree and not search to the entire depth of all possibilities. Okay. The sequential algorithms, one of them I described the forward search, where you take a feature and add it one by one. And we can do this going forward or coming backward, as we will see in the next few slides. These tend to be trapped in local minima, meaning we may converge to a value and accuracy that's not the best value. So there may be a combination that we will not be able to discover when we do a sequential algorithm. Okay. So we make some committed steps, committed decisions early on that may affect and the outcome of our search, but we may not explore a combination that is more promising. The randomized algorithms are the preferred algorithms if you have the time to run them. And genetic algorithms is sort of, a state-of-the-art randomized algorithm that you can employ for feature selection. Okay. So this graph shows selection of 4 features. The top node shows the selection of no features. So I'm going to base my classification on an empty matrix where I have no measurements. Okay. The first level describes selecting one feature. So selecting the first feature, using the second feature, third feature, or the fourth feature. Okay. The next level captures selection of pairs of features. So 1 and 2, 1 and 3, and so on. 3 features, and finally 1 feature. Okay. A walk from top to bottom is a sequential forward search. A walk from bottom to top represents a sequential backward search, or another name for this is recursive elimination. Okay. What does this mean? I'm going to start with no features at hand. I'm going to try using one feature, which one gives me the best result. If this one is the best result, I'm going to keep it. And then I will, starting from here, test these 3, which means in combination with the third feature, which ones of these 3 will give me the best result. Okay. Should I use the first feature in combination with third, or should I use the second feature in combination with third, or should I use a fourth feature in combination with third? Okay. So these edges sort of represent pairings with the third feature. And among those 3, let's say this one worked best. So I'll keep this one, keep the third one and the first one, and then ask the question, which one do I add next? Okay. So I'm going down the tree until I add them all. All right. You usually would not go all the way down to the bottom. You could. If you do, then you're going to get, say, 50%, 80%, 85%, 70%, 60%. Right. So the accuracy does not necessarily increase as you go down. Okay. The machine learning method you use would usually decrease in accuracy. So at the top, it's going to have low accuracy. At the bottom, it'll have low accuracy. Somewhere in the middle, you're going to have a higher accuracy. Okay? So we would like to find out which node in the middle has the best accuracy. So this is a sequential forward search. On that graph that I showed, you make a walk all the way to the bottom. And then you can optionally stop if your objective value saturates and doesn't improve anymore. So you can look at your graph of, say, accuracy values as you make your walk. So with one feature, let's say our accuracy improved. Second feature, our accuracy improved. Third feature is stayed constant. Fourth feature is stayed constant. And fifth feature decreased. So you don't have to keep going. You already know that it's converged. And you're going to have some conversion mechanism to capture that. If your accuracy doesn't change or goes down, that's when you can stop and not search any further. And we'll just use these 2 features. Okay? Make sense? So you can implement a stop criteria. That way, your algorithm terminates faster. Same thing with the backward search. Again, you can stop if your objective function, if the thing that you're optimizing for doesn't improve anymore. Okay. All right, so the comparison of forward search and backward search. Forward search works well when the best possible subset is small. All right, you may not know that beforehand, but if it does happen to, if the problem does happen to have an optimal subset that's small, SFS is more likely to discover it. Okay. SFS is also more computationally more efficient because you are starting with smaller matrices. Okay. You're starting with a matrix of size 1 rather than a matrix of size 100. Makes sense? And assuming that you don't go, or even if you go all the way to the end, you would be saving a lot of time by not exploring all these three, right? So this one is a 3-dimensional matrix. You have 3 columns. Here you have 1 column matrix. When you're running SVM, if you just have 1 column matrix, you're going to train it faster compared to 3 columns. In a larger example, 1 column will run much faster than, say, 1,000 column matrix. All right. So for problems like SVM neural network, where the computational resources is highly dependent on the number of features you are using, using forward search would make more sense. All right. And SBS may find a better accuracy because you are starting with all of them in the set, but you're going to end up with a subset that's large. So it will have a tendency to have a larger feature set rather than a smaller, more minimal set of features. Okay. So the limitations are that SFS is unable to remove features that become unuseful as you iterate over the search space. What I mean by that is, say I've added this, and I've added this. I'm only following the arrows that this would take me to. Okay? If this was the best option at the first level, I'll never be able to explore this node, right? But say it's 2 and if this combination 1 and 4 is much better, I'm not going to be able to discover it because once I commit to using the 3rd feature, I'll never go back. I'll never undo that 3rd feature. Okay. So that's a problem with forward search. And you have same problem with backward search. Once you remove a feature, you will never reconsider that feature again. Okay. And it may happen that that feature that you removed early on ends up being useful in combination with other features that you end up having later on during the search. So some variations to overcome these limitations are bidirectional search, where you would search both from the top and from the bottom, plus L minus R selection, which is a more general way of performing a forward or a backward search, which we will see next. So in bidirectional search, you simultaneously go forward and backward, and you select features using SFS, and you only select them if they are not removed by the backward search. And likewise, you remove features that are removed by SBS and that are not added by forward selection. So you sort of look at it from both ways. And plus L minus R means I'm going to walk down L steps. I'm going to add L features. but then I'm going to do a backward search, remove R features. Okay? So let's look at this figure again. Imagine I'm having a much larger graph. What I'll do is say I'll add 2 features. Doing forward search, I go here. And then I'm going to ask which ones of these should I remove doing a backward search. And it's going to walk back. And then add 2 features. And ask which one should I remove backward. Okay? So the search becomes like a walk that looks like this figure. You say you add 10 features doing a forward search. You remove 5 features doing a backward elimination. Add 10 features forward search. Remove 5 doing backward elimination. Until you get to the bottom or until your objective function converges. Okay. A more advanced version of this is sequential floating forward backward selection, where the L and R are done dynamically in a way that rather than committing and saying I'm going to remove 5, you will only remove up to the point where the accuracy does not decrease. So you don't preset L and R. You let them be decided dynamically as you walk up and down. Okay. So rather than saying I'm going to add 10 and remove 5, you don't have those pre-defined numbers. You're just going to walk until things stop improving, and then you're going to backward eliminate until things stop improving, and then do that back and forth. Okay. All right, and that allows you a more sort of complete, a search that's more promising to find the best possible subset. The final method that I'm going to describe is genetic algorithms. In this method, as one of you described in your topic presentations, we model the problem as a genetic optimization problem where each possible solution is an individual. This is one individual. That's one individual. Everything here is one individual. But generally, the problem is going to be more complex than just 4 features. So if you have 100 features, you're going to have 2 to the 100 possible individuals. Okay. We wouldn't list them all. We will just have a sampling of them. Say we're just going to write down 1,000 such individuals out of 2 to the 100. Okay. So at each population, we're going to have 1,000 individuals that are things like this. Okay. So I'm going to have a smaller subset of all these possible solutions. Okay. And the population can be, in this case, described as a matrix with 1,000 rows, 1,000 columns, 100 columns, and 1,000 rows. Okay. I have 1,000 individuals. Each individual describes whether or not they will use the first feature, whether or not they will use the second feature, and so on. It's a binary vector describing which of the 100 features they will use for classification. Okay. And what I'll do is I'm going to go, say, to SEM, and from my data matrix, only use the features that this individual wants to use, and ask what's my accuracy, say 80%. Okay. Again, you have to do cross-validation to get that number. For my second individual, which uses a different subset of the features, I'm going to ask the same question: what's my cross-validation accuracy for this combination of features? 70%. Okay. So this number here is going to be my fitness value. All right. The fitness value is how I will make a selection from these individuals. This is one population, one generation. So my goal is to take the individuals in this population, take them to the next generation in a way that will take me to a more optimized set of population. So I want to create new individuals that will have better fitness values. Okay? So the idea for the strategy that I'm going to use comes from natural selection. It doesn't make sense to take the ones that have low fitness value. Right? So if someone scored 5%, I'm just going to kill them. All right? If someone scored 90%, then they really have something going on for them, I'll keep them. Okay? And the selection is done in a weighted manner. Let me see if I have using this Russian roulette selection, just a roulette wheel selection. Okay, so what you do is you using the fitness value, you create this fortune wheel of fortune. Okay, and the angle of the pie, the section of the pie will be dependent on the fitness score. Okay, so if this the individual 4 scored highest, 52, you're gonna give them the largest piece of the pie. Okay, and then you're gonna roll the wheel, and then whoever gets to be selected, this is more likely to be selected, but everybody gets a chance. Even the 5% can get lucky. All right, they'll survive into the next generation. All right. So it's a better approach than saying I'm going to kill 5%. So 5% may have some selected features that may give us better accuracy later on in combination with things that they don't have. Okay, so that's the selection strategy. And then the crossover idea is to combine the parts of the solutions in the hope that when you combine 2 solutions, you may come up with a better solution. And the way you do crossover will be problem dependent, depending on how you model the genetic algorithm problem. You may end up doing different types of crossovers. But for feature selection, you can essentially take one individual, 1, 0, 1, 1, and so on. Take another individual and make a cut, say after the second feature, and then combine the 2 parts to create 2 new individuals. So from the first one, the first individual tells me that I'm going to use the first feature, don't use the second feature. I'll take that, combine it with whatever features this part dictates me to use. That's going to be my 1 new individual, and the other combination will be the other individual. Okay? And if you want to enforce every couple to have just 1 child, you can kill the child that doesn't have good fitness value. Right? So if out of the 2, one is better than the other, you can keep the one that's good. All right. Sometimes you do these things to keep your population size in check. Okay. All right. So crossovers may not be sufficient. You want to add some variation to the population. Okay. Your initial population may not really have all the possible options, and it won't, because we have to do the power 100. So you want to be able to explore things that are not present in your current population. Crossover is one idea, but it's not sufficient. It still is restricted to using parts of the solution that you have in the population. So to explore the parts that are not present, you want to mutate the individuals. And for this feature selection problem, a mutation is essentially taking one of your numbers and flipping it. If it's a 1, we'll make it a 0. If it's a 0, we'll make it a 1. So randomly pick a position. If this individual says use that feature, we're going to create a new individual that says don't use that feature. Okay? So doing crossovers, doing selections, crossovers, and mutations, we get a new population of 100 individuals that hopefully perform better than the previous generation. And then we're going to keep repeating this, create a new generation, following these operations. And you may have a preset number of iterations, number of generations, or you can stop when the fitness values converge to a certain value. Okay. So you may stop when you are happy with the current fitness value, or you may stop when a fixed number of generations are reached. You may stop when you've spent enough time waiting on your computer. That's another option. And then when you do stop, what you would do is you can look at the last population and use the one that has the best fitness value. But what you really need to do is, as you are iterating over this algorithm, you have to keep the one that performed best in any generation, right? Because the one that performed best, say at generation number 3, may get mutated and you may lose that fitness value. So you want to keep track of the best performer across all your generations. Okay? All right. A lot of the programming languages will have a genetic algorithm implemented for you. So what you would then do is define your function that would evaluate your individuals and also define your solutions. So sometimes in the feature selection case, a binary feature vector is sufficient. In some of the other problems that you would employ genetic algorithm, you may have to craft other vectors to represent a solution. Okay. All right. So let's see, MATLAB. So if you search Google for genetic algorithm for feature selection, you're going to see some examples. You will also be able to find some files on File Exchange that do that for you. Okay. So when we did support vector machines, SVM demo. We defined this function that evaluated a given set of parameters, right? What you would now do is write a similar function and then be able to, say, change the selected features. So let's say selected features is going to be a binary vector. And when you use X, rather than using all columns, you're going to use only those columns that are asked to be selected here. Okay. So you can create a function like this, or just create a new file where you have this function, and then provide this as the fitness function to your genetic algorithm. Okay. All the other things in MATLAB genetic algorithm package should work as is. The only thing that you need to specify is how many total features you have, which is going to be the number of columns in your data set, and what the evaluation function is. I'm going to use support vector machines to do cross-validation, and the accuracy I get will be the fitness value. Okay. You may have to worry about whether the genetic algorithm maximizes or minimizes, and I think it maximizes. So you would have to take the negative of this, because k-fold loss means it's bad. Minus would mean it's good. All right. So you want to minimize the error. You want to maximize the negative of that. Okay. So what I'm going to do for feature selection is I'm not going to show you in MATLAB. If you want to do it in MATLAB, Sequential FS. Let me open MATLAB and show you the function. If you were to do this in MATLAB, there's a function called Sequential FS. Let me go down to the examples. You can look at this example. So for this Sequential FS function to work, you need to specify an evaluation function that the Sequential FS can call. All right? So this function needs to take 4 things. And you can either do it on the fly or you can create a new file for this. You need to provide xtrain, ttrain, right, smaller, xtrain, ttrain, xtest, ttest. So if I were to do this for support vector machines, let's say this is my evaluation function. I would train the SVM. I'm going to call it SVM train on xtrain and ttrain. And I get my SVM model. Right. And then I will apply xtest to the model and get my y-test, my predictions for this test set. Let's say model.predict. The exact syntax may be slightly different, but this is the idea. I'm training the SVM on the pair of training set and the training targets, and test it, get my y-test, and then compare my y-test with my t-test. And the last value is going to be the fraction of times that I made a mistake. Okay. So if this is just a single column target, you may have to do this y-test greater than 0 or greater than 0.5 if your targets are 0 and 1, right? Equal t-test. That's going to be that. This expression will tell me whether I made a correct prediction for each of my test cases. Then I would take the average of this, or let's say not equal, to find the number of times I made a mistake. Okay. So this is the fraction of times that I made a mistake, and I will return this from the function. All right. So the sequential FS will call this function repeatedly. So MATLAB's sequential FS is responsible for implementing that search that I showed you in that graph. What it will do is it will look at your X matrix and then look at each feature individually. It's going to call your function with eval is not really the function that I want to use. I'm going to call it my eval because MATLAB already has an eval function. So I'm going to do my eval with the training subset. So it's going to do cross validation. So for the first training subset, we'll say all features, sorry, all rows, all samples in the training, comma 1. I'm using just the first column. And then ttrain. And then all features in the test set, comma 1, sorry, only the first feature, but all samples, and then t-test. The target values for the test set. And then your function will return a value that will say, this is how much mistake I made by using the first column. Say, so this is not accuracy, it's mistakes. So 90% of the time I was wrong. 10% of the time I was correct. Then it's going to repeat the call, and then it's going to do this, say, k-fold times if you're doing k-fold cross-validation, 4-fold cross-validation, for example, it will call this 4 times and take the average. Okay. Then it's going to now ask same thing, but now with the second column. Send to your function, get the answer, do this 4 times, take the average, then it'll get, say, 80% in this classification rate. You'll do this for every column, and then pick the best one. Okay. Then it's going to take that, put it aside. Say the second column was the best in the first round of tests. And it's going to come back and say which feature in combination with the second one, 1 and 2. If I were to use the first one in combination with 2, what is my loss value? So we've already selected 2. We're not going to test it again. In combination with that, the loss is 0.7. And then in combination with second, if I were to use the third column in combination with the second, what is my loss value? And then it's going to give an evaluation for this column. Look at which one is best, take it, set it aside. Now that one is selected, move on to the next feature to select. Okay? Well, as I said, you don't have to worry about all this. MATLAB will do that for you. You only need to worry about how you evaluate for a given training set where it will contain some of the columns from your original data set, but you don't really care which ones. Sequential FS will throw different combinations of columns to your function. Okay. All your function has to do is train your model, SVM or neural network or whatever it is, and test it and report back the misclassification rate. Okay. Make sense? All right. What I will do instead of demonstrating this in MATLAB is show it in Python because we didn't do anything in Python. So if you had class last week, I would have assigned them Python homework, but since we didn't, I'll just show it to you. So I emailed, if you don't have Anaconda, you can install it and download this feature selection.diabetes.ipynb and go over it yourself if you'd like. Okay. So for this demonstration, I'm going to use the Pima Indians diabetes dataset. It's available in the UCI database. The classification is to predict whether an individual has diabetes from the following features. So we have 9 features, and we are trying to predict whether that person has diabetes or not. Okay. And the goal here is going to be, I don't want to use 9 features. I want to find out which subset of these features would give me the best prediction rate. Okay. If you just throw all these to an SVM model, it'll give me some accuracy, but that accuracy will not be as good as if I were to provide to SVM a smaller subset of these features. Okay? I want to find out those smaller subsets, that smaller subset. Okay? Some utility functions that I've defined. So this is download file. If a file has not been downloaded before, it'll download it. Print file head truncated is going to print the contents of a file. So if I say, show me the top 10 rows of a file, I can use this function. Okay? Cross-validate is a function I can use. It'll call a classifier repeatedly and report the cross-validation with 4-fold cross-validation. Okay? The package, in Python, things are organized in packages. You have to install the package if it's not installed. So the machine learning methods are availavailable in the sklearn package. Okay. All right. I'm gonna call the cross-val score with that classifier. That classifier could be a decision tree. It could be a support vector machine. But the process that I use to perform cross-validation is the same, right? I'm gonna train it. I'm gonna test it and compare the predictions with the correct outputs, right? So everything that is relevant to cross-validation are kept in this cross-val score, and the classifier captures which type of machine learning method I'm using, and they report the fault for cross-validation accuracy, which I'm just printing it out. I'll return it as well, but let's not bother. Okay, so I'm going to demonstrate a few machine learning methods here. One is decision tree. The other one is quadratic discriminant analysis. So this is not linear; it's quadratic. We did a homework. You guys did a homework on both linear and quadratic discriminant analysis. And I will also show support vector classifiers. And for speed, I'm going to use a linear kernel. Right. The reason I'm using a linear kernel is I want my feature selection to be each evaluation of if a feature subset should be fast, and I want to have to wait a long time for a more accurate kernel to evaluate. Okay. If the data set is not present, I'm going to download it, and then I'm just showing you the first 5 lines of data. It has 9 columns plus the target, whether or not each patient has diabetes. Plug myself in. What do I do next? So this is a text file. In MATLAB, you can use functions like table read. If it were an Excel file, you would use XLS read. In Python, we are going to rely on a package called pandas, which has file input functionalities. It can read text files, it can read Excel files, and what you get is sort of a data matrix where your numerical data is part of the matrix, and you also get column names as part of your variable. You don't have to keep it separately. Good time. Next year. Okay, Tuesday. Off. I want to put that. Okay. All right. So I've loaded my data. The data doesn't contain the names of the variables, the attribute names. I hard coded these. I looked at the UCI data set where these names were described, and I just gave each column a short name and created the pandas data frame. This data variable is going to contain the information that's read from the file. Right, these numbers plus the column names that I have hard coded when I created the pandas array. Okay. Data.head just tells Python to select the first 5 rows from this data matrix, and it'll print out the first 5 columns. Sorry, the first 5 rows. Okay. So it has a lot more patience, but we're just going to show the first 5 as an example. All right. So next step is to separate the data into your X matrix and your target, similar to MATLAB, but this is the syntax I would use. I'm going to select all rows, and colon -1 means if you were to do this in MATLAB, 1 to n -1. Okay, so that's Python's way of saying 1, starting from 1 all the way to n -1. Right, and the target is going to be just n -1. All right. And the names of I don't want to keep has diabetes as a name. I'll keep just these as my feature names. Okay. So let's look at the base classification where my classifier has previously been defined as a support vector machine classified with a linear kernel. So I just call the cross-validate function. It'll take my support vector machine classifier, train it and test it on the X matrix and the target values using four-fold cross-validation. And the results are printed out at 76.3%. And you also get the standard deviation because you did 4 cross-validations. It will show you the average, but it will also show you how variable they were across those different 4 runs. Okay. So next, I'm going to use a filter method to make a selection of the features. There are a number of features, there are a number of filters, definitions of filters that you can use as listed on this website. Okay. So on the table that I showed you, some of them are implemented here. For this particular example, I will use using chi-square test, and I'm going to ask it to return me just 3 features out of the 9 available in the data set. Okay. I'll just say select k-best features using chi-square method and get 3 methods, and then apply it to this particular data set. So I'm creating my selector, feature selector, as an object, and I'm applying it to this particular data set. And then there's this Python syntax, Python tricks to just print out, sort and print out the features according to their chi-square measure. Okay, so the best feature is using insulin, and it has a chi-square score of 2000. Using glucose is the next best feature, and that's the score of 1400. Okay. If you just want to use the first 3, you would use insulin, glucose, and age. All right. The problem with the filter approach is that insulin and glucose would presumably have overlapping information, right? So if you use insulin, even though glucose is the next best thing, it may not be the next best thing in combination with insulin. Okay, so we would be losing on that piece of detail if we were to use a filter method. But regardless, let's use top 3 features selected from this list and see how well it performs in support vector machines. So when we did not do any feature selection, we had 76%. When we just use the 3 features, we get 73%. Okay. So sometimes you may increase, sometimes you don't. This was just a demonstration. All right. So now let's use a different method to make a selection of the features. We're going to use recursive feature elimination. We're going to start with all the features included, and we're going to ask which feature should I remove and get a better accuracy. And we'll repeatedly ask that question until things stop improving. Okay. For this, I'm going to use logistic regression classifier, because I think when I tried SVM classifier, it was still taking a long time. I'm going to use a faster method using logistic regression. Okay. Using feature selection in Python is in sklearn package is pretty straightforward. You provide your classifier method to RFECV method, which stands for recursive feature elimination, with doing cross-validation, and we're asking it to do four-fold cross-validation, and the scoring, we would like to use the accuracy. Okay, so you can say use sensitivity or some of the other options that it may have, but for this, we're just going to say try to improve accuracy as you are doing feature selection. Okay. And then we are going to make a selection and then report the selected features using this syntax. And the selected features, it ended up selecting 5 out of 9. Number of pregnancies, glucose, diastolic, BMI, and pedigree. Those were the selected features. Okay. They are, I believe, they are not necessarily in the order of selection, in the order of importance. Okay. So it doesn't mean that number of pregnancies is the best one to use. these 5 in combination survived the selection area. Okay, what am I doing next? This is really number of features selected or removed. This may have the reverse meaning. But let's just keep going. I think no, number of selected features. Okay, so this selector represents the history of the selections. Okay, and as it is performing a selection, this is number of features removed inside the elimination. Okay, as it's going to start with 9 features, it's going to remove 1. Okay, when it removed 1, it had 66% accuracy. When it removed 2, it had 68% accuracy. So all this historical information it kept in this in that variable, in that selector variable, and you can access the scores in that grid scores property of the selector. Okay. So this is a typical graph you would see when you do feature selection. As you forward select features or as you eliminate features, your accuracy will increase. If you use a method that stops selection, it's going to saturate, and then you won't see the end of it. If you say run all the way to the end, you would then see it dropping off again. Okay. If you were to go say all the way to 9 features, you may see a drop. All right. Make sense? Okay. And with logistic regression and and these selected classifiers, we get 76.7%, which is not much different than this because we use a less powerful method for performing the classification. Okay. If you were to use support vector machines, you may have a slightly better prediction rate. So this is a small toy example to demonstrate the coding and the concepts in Python. The difference that you will see in accuracy before and after feature selection is going to be more significant when you have many more features. If you have 1,000 features, then the amount of accuracy improvement is going to be more significant. Okay.